Hi guys, my name is Sergey and you're watching Dissecting the Code. Today we're dissecting when a local instance becomes eligible for GC in C#. And spoiler, it's not always when you think it is. Okay, when you think about the CLR, the first aspect that comes to mind is memory management. One of the biggest selling points of managed environment is the fact that you should not care about explicit deallocations, double cleanups and other issues. This is true most of the time, but there are cases when you still need to think about memory layout or avoid excessive allocations or just be careful to avoid memory leaks. Okay, let's start with a very simple practical scenario. Imagine you're reviewing the following method. You have a method that creates a local variable called processor, then it calls ProcessRequest to process the data, then it sets the local variable to null, and then the method has a bunch of work that might take time. So the question is, does it make sense to set the local variable to null? Essentially, the question is, when a local variable becomes eligible for GC? At the end of the method? At the end of the scope? Or maybe even sooner? The simplest way to see how GC works is by using a class called WeakReference. A typical local variable creates a strong reference, and if the instance has any number of strong references, it cannot be collected by the GC. But if it has 0 strong references but any number of weak references, it can be collected. So we can force the GC collection by calling GC collect, and we can trace if the instance is alive or not. So let's run this code. And we can see that the instance is still alive. Okay, we're running in debug mode. Maybe this is the problem. We can try to run it in release mode. Okay, the same thing. Now let's try to set the local variable to null. And it's still alive. Interesting. Go. In this project, I'm using .NET 9. And starting from .NET 3.0, the runtime uses so-called tiered compilation by default. In every JIT-based environment, there is a constant battle between the efficiency of the generated code and the time it takes to generate it. And tiered compilation kind of makes this battle more flexible. JIT tracks how many times the method is called, and when the call count crosses a threshold, the method is re-JITted, recompiled with more optimizations. And Tier 0 compilation prioritizes compilation speed over code execution speed, which kind of does make sense because some methods never called more than once. So it generates code quickly, but often skips more complex optimizations like precise tracking of when the local variable is last used. There are multiple options how to enable all the optimizations. One is target full framework, for instance. Another one is to go to project settings and disable tier compilation altogether. Another option is to call this method 10,000 times. And the last one, the simplest one to use right now, is just to use a special attribute called method impl and tell the JIT to use all the optimizations from the get-go. Now we can test this. So if we run this code, we can see that the processor is dead. Cool. Now let's see what's going to happen if we'll comment this line out. And we can see that the processor is dead again. But how and why? So how the GC knows when a local variable is eligible for garbage collection? So actually, JIT compiler tells the GC when a local variable is no longer used. And it tells the GC this via data structure called GC info. You can see this information in the JIT output, but the trick is that you cannot just look at disassembly from sharplab.io or from benchmark.net. To see this information, you actually have to use a debug version of JIT and specify a few flags. The simplest way to do that actually is by using a Visual Studio plugin called Disasmo. And this plugin is written by one of JIT devs, and it's very helpful and useful in such scenarios. And in this case, to see this information, we need to build a runtime locally. In this case, it's very simple. You just git clone this into your local folder, and this plugin will nudge you and tell you how exactly you need to build this. And after that, you need to specify one setting. Essentially, this .NET JIT GC dump equal, and this is our process request star, so it will dump all the JIT information for the methods that starts with process request. And now if we'll just run the disassembly, so let's see that, it will compile our executable. So in this case, the output is quite complicated. So the simplest way to do that is we'll simplify the code a little bit, and just because I don't speak assembly as well, and so let's do this again. Okay, here you go. So typically, this is how a JIT output looks like, and you won't see this information. And because we're using a debug version of JIT, we see this as well. So this is this GC info that allows the GC to know where the instance is alive or not. The important information here is that it tells at which offsets in this assembly code the instance is alive or not. And essentially, it's just two places, from offset 12 to 17. This is when we're actually creating an instance. And then this is low-level assembly, so we call an object constructor manually here. And this is another place where the instance is eligible for GC. And this is very tricky, because we cannot see that the ProcessRequest instance method is covered by this segment. And this is by design. So for every method called, and this reference is stored in one of those registers. And when the GC runs, it checks if registers do have references to our instances, and registers do consider to be root references. So, and in this case, what we can do is we can go even further and do some tricks here. So let's do this. Let's have an instance method that will do some, it will touch an instance state and then nothing else. And again, similarly to the previous case, we will force the GC and we'll see if when the instance is collected. So let's run this code. Okay, and it shows that the instance is dead before finishing process request. So it means that at this point, this instance was collected by the GC. How and why? Okay, this is quite similar to a previous code. Every instance method is essentially, you can think about this as a static method that takes this as the first argument. And it means that if this is no longer used, then this instance can be collected by the GC even when the method is running right now. But that's not it. So what if this method can be inlined? And what if this method does not touch an instance state? And in this case, it seems like it might be eligible for GC even before the method is called. And we can do that. And if we'll trace this case, let's see what's going to happen. So we can see that processor is dead even before the instance method is called. And again, if we'll check the assembly code, we will see exactly the same thing. So the instance was only alive from the GC point of view when the instance was created. And later on, it's just useless, and it might be eligible for GC. It's mind-blowing, but this is the case. The instance can be collected when the instance method is called, and in some really strange cases, it can be collected even before the instance method is called, if that instance method actually can be static. Does it mean that you should never set local variable to null to affect the lifetime of a local variable? Okay, let's explore one last thing. Let's look at async methods. Let's say that the processing part is synchronous, but the method where this processing is happening is actually asynchronous. It has an await at some place, and it potentially runs for a very long time. So does it make sense to set the local variable to null in this case? Okay, let's see. So right now the processor is dead. Okay, but let's say that the code changes, and now we have an await in between where the local variable is created and local variable is used. So now let's see what's going on. Okay, now the processor is alive. And now let's set it to null. And now the processor is dead. Okay, so now this actually changes the behavior. The ID tells us that this is not necessary, this is a bug, and I filed a bug report on GitHub. But let's explore what's going on. So let's get back to our old state, let's compile the code, and let's look at IL to understand that. So local variables in async methods might be real local variables, like this one, if they are used between awaits, or in this case from the start of the method to the first await. But if you add await in between, then the code generation changes and the processor is no longer a local variable, it's a state in the generated state machine. And the state machine is alive for the duration of the entire method. And that's why when we actually set it to null, then this actually has an observable side effect, because this sets a field to null, which changes the lifetime of this instance. Okay, as you can guess, .NET memory management is quite a complex topic. And so what we've learned today is that for the synchronous code, don't set local variables to null. The JIT and the GC can take care of that. In case of async methods, yes, there are legitimate cases when you can set it to null to affect the lifetime of a local variable. But again, please be careful and understand what you do. If you enjoyed that deep dive, hit that like button, subscribe, and let me know in the comments below what .NET topic you want me to cover next. That's it for today, guys. Thanks for watching, be curious, and see you next time.